Hello, this is Jude Socrates. Welcome to my video series on multivariable calculus, known as Math 5C at Pasadena City College. Maybe you noticed we have a new cover page. Check it out. I put in a couple more diagrams at the bottom. Woohoo! So there they are, or were. All right, so that's actually the same solid, and you might remember this was one of the examples on double integrals where we found the volume of this solid, basically the double integral of this sine function over a rectangle. So those were three of the views from that topic. So we also have a milestone today. This is video number 20 for our series. And I don't think we're even halfway there. So who knows, maybe there will be 50 or so videos by the time all is said and done. I don't know. I haven't really planned it ahead. Haha. All right. So today we are going to continue with triple integrals. We're basically going to do one thing. We are going to change the order of integration in a triple integral, and we are going to walk step by step through the example that you find in your ebook. So I will see you in a minute on page 148. All right, so here we are. But the main difference with what we did in double integrals, exchanging the order there, is that we're actually not going to integrate anything. We're just going to change the order of the integral signs and the corresponding differentials, of course. But there won't be an actual function that we are going to integrate. At least not for this video. Maybe in your homework, haha. Okay, so this is the problem that we are going to walk through. Okay, we have this triple integral from -2 to 2 dy of integral from y squared to 4 of dx of integral from 0 to 3x over 4 of dz. And we have this unknown function inside. So we are going to change the order of integration. Okay, so there will be 5 other orders, 6 total. So I'm going to walk you through step by step on how to do it. All right, time to get to work. So the first step is very easy. You already know it. We're just going to label the integral symbols with the corresponding variable. Okay, so dy is our outer, so y will go from 0 to 2. Dx is our middle, so x will go from y squared 4, and z will be on the inside, so z will go from 0 to 3x over 4. Okay, so now is probably a good time to mention or remind you that the symbols that you put in your integrals are very sensitive. Okay, on the outer integral, you can only have constants, never variables. Okay, so you can't have something like 0 to z on the outside dy. That doesn't make any sense at all. Okay, so y will go from the constant -2 to the constant 2. Okay, our middle integral is in dx, so x will go from y squared to 4. And notice that the symbol here, y squared, that's the variable of the outer integral. Okay, so again, it won't make any sense if you put z squared over here, okay, because z is the inner differential. Okay, so the middle can only depend on the variable of the outer integral. In this case, that's y. So y squared is perfectly valid. The innermost integral can depend on one or both of the variables in the 2 outer integrals. Okay, so z can depend on both x and y, or only x or only y. Okay, so we decided here, or I decided for this problem, that z will depend only on x. Okay, if that were 3y over 4, that would also be perfectly acceptable. Okay, but of course the problem will be, I should say, completely different. Okay, so z will go from 0 to 3x over 4. All right, so the first step, I already wrote it down to save a little time. Here it is. Okay, so let me refresh that a little bit. Why did you truncate down there. Let me try the other side. Okay, there you go. Okay. So y will go from -2 to 2, x will go from y squared to 4, z will go from 0 to 3x over 4. Okay, so now let's go to GeoGebra, and we're going to draw these three surfaces. All right, there's our standard view. So I hope, okay, there you go. I was a little worried that it will draw a line instead of a plane. There's y equals -2. And then we have y equals 2 over there. Okay, so that is our interval for the y. Okay, there's a y-axis. Y will go from -2 to +2. X will go from y squared to 4. So let's type in x equals y squared. There it is. Okay, so it's a parabolic cylinder. There's x equals y squared. And of course, we only want the part between -2 to 2 along the y-axis. So we can basically ignore anything beyond, I guess, these two lines. Okay, because we are going to end at x equals 4. Oh, guess what? Yeah, that's where the cylinder exits beyond this interval. Okay, so with your permission, I can therefore remove now these two planes, because we know we're going to stay inside this region. Okay, so remember, the outer double integral creates for us a domain, a region on the plane. Okay, and because our variables are y on the outside, x in the middle, those two form the xy plane, those two variables. Okay, so this will be our domain in x and y. Whoops, can't see it. This parabolic plate. Okay, so I think it's safe to remove these two planes. Okay, we know we have to be inside this region. Okay, excellent. So actually, as a matter of fact, okay, look at, here's the x-axis, here's the y-axis. That is our domain in x and y. Okay, if I tilt it too far, we won't be able to see it. See, disappear. Okay, but okay, so there you go. You can still kind of see it. Here is x equals y squared. We end at x equals 4. Okay, so this is our domain. I have a diagram of that in our PDF ebook, of course, but I did draw it only in 2 dimensions. Okay. So we have our final surface. Z goes from 0 to 3x over 4. So of course, z equals 0 is the xy plane. So maybe we'll just select plane. So what we need is the part which is above the xy plane. Okay, and we're going to put one more plane, and that is the plane with equation z equals 3x over 4. Ta-da! Okay, so there is the final side of our solid. Okay, so yeah, it doesn't, of course, look very clear. If you are looking ahead in our ebook, of course, I have a much better diagram there, which I am going to show to you. Okay, so we know the top view is a parabolic plate. Okay, it's still there. The bottom is the xy plane. The top is this inclined plane. Okay, so it's like a wedge, right? Very similar to the solid in our last video, because that is a twin sibling. Okay, what do I mean by that? This plane and x equals 4 seems to intersect at z equals 3. Oh, look, if x equals 4, z is equal to 3. Okay, so the solid up here, that's actually the solid from our last video, except it's upside down. Okay, so I like to think of them as like twins, okay, fraternal twins in this case. And check it out. This solid has something extra. Okay, there's another side over here that looks like a rectangle. Okay, And as we're about to see, yep, of course, it really is a rectangle. Ta-da! So there is our beautiful solid. This is, of course, exactly the same source, GeoGebra source that I used to create diagrams, the screenshots for the PDF. Okay, so from the top, okay, so this time it won't disappear. From the very top view, here's the x-axis, y-axis. We have our parabolic plates. Okay, so actually from here, we can easily make the second order of integration. The first one was y outside, x inside. Okay, now we can do x inside, y in the middle, I should say. Okay, so check it out. X is going from 0 to 4. Okay, and then y, okay, so here's the tricky thing. Y will go from low to high. So y will go from this half of, what was this, x equals y squared, to this half of x equals y squared. Okay, so that is y equals positive square root of x up here and negative square root of x down here. All right, so we're back in our PDF, and this is our second order of integration. X goes from 0 to 4. Y goes from the lower half, negative square root of x, to the upper half, positive square root of x. Okay, and compare that to, yes, it fits our original problem, which is here. Notice that the innermost integral does not change at all. Okay, because all we exchanged are the two outer differentials and the two outer integral signs. Okay, so yeah, obviously, first thing to notice, we don't just exchange these two things. Oh, we're done. It will not make any sense at all to have x equals y squared to 4 over here. What did I just say? The outer integral can only contain constants, numbers. You cannot have symbols on the right side of the variable in the outermost integral. Okay, you can only have constants. Okay, so let's go back to GeoGebra and we will look at the next two orders of integration. Okay, this is where we left it off. We were looking at the top view, so now we can go back to our three-dimensional perspective. There you go. Now it's back to being a solid. So what's our next order of integration? We did the top view, so we have two other views, the side view and the front view. Okay, we are going to go next to the side view. Okay, so side view, we will put, okay, so remember this time, we're going to stand on the negative y-axis so that the positive x-axis is to the right, the positive z is going up. Okay, they have to be positively oriented. Okay, so we're going to turn this until we get the side view, which is right over there. This is always the trickiest one for me. Okay, I am just going to try to get it to be as close to center as possible. Yeah, I have a trick actually. Let me show you. I go to standard view. There we go. And if you do that, then it usually behaves better when you, there you go, when you rotate it. There, okay. I was supposed to be a surgeon. No, not gonna happen. So there's our side view. It's a right triangle. Okay, so that's expected because here we have that plane x equals 4. And here we have the other plane, which was z equals 3x over 4. So yeah, we have z versus x. Okay, so now we're ready to set it into the next two orders, which is you can go x first. So x will go from 0 to 4. And then z, okay, so now we will scan it as a type 1 region. Z is starting at 0 at the bottom and ending at that plane, z equals 3x over 4. Okay, so that's as a type 1 region. How about for a type 2? Okay, so we're scanning left to right. So we already said that the z-coordinate at 4 is 3. So 0 will go from 0 to 3. Okay, where do the arrows enter? They enter on this line, z equals 3x over 4. Solve for x. So x equals 4z over 3. Okay, and all the arrows end on the right here as x equals 4. Okay, so those are the limits for the double integral. Okay, we still have the inner integral. Okay, and that's where we have to do something new. Okay, so what do? We scan with arrows. Okay, so this time we are the one shooting arrows through that solid. They're going pointing towards the positive y-axis. Okay, so I believe, yes, those are the arrows that I have made. Pew, pew, pew. Oops, not that one. Okay, so we have these 3 green arrows. Okay, so yeah, I colored them in case you haven't noticed. I colored them the same axis, same color as the axis that they are supposed to be parallel to. Okay, so the arrows enter through the parabolic cylinder, the bottom half, and exit through also the parabolic cylinder, but this time the upper half. So yeah, in all honesty, if you go back to the top view like we had before, that should remind you of our type 1 test, right? Does this happen all the time? I don't want to say yes, okay? You really have to look at each and every view to make sure that what you think is happening really is happening. And I can already tell you, no, it's not going to happen like this all the time. Definitely not. All right, so here are our next 2 orders of integration. I'm deliberately sitting over here to hide this diagram. We'll see it in a little bit. So remember, our domain was that right triangle. We said that x is going from 0 to 4. Z is going low to high from 0 to 3x over 4. Y, the green arrows, entering at negative square root of x, exiting through positive square root of x. Okay, so the inner integral stays the same in both orders because we're only exchanging the 2 outer differentials. Okay, so we said now z is going from 0 to 3, and as we scan left to right, x is entering at the plane. So solve for x from this equation. X is 4z over 3, and exiting on the right vertical leg at x equals 4. Okay, so we have 2 more orders of integration, and that is going to come from the front view of the solid, saving the best for last. Okay, so we're ready for the front view. I'm going to hide our green arrows over here. Front view, turn this way, and you need to be on the positive x-axis right there at the front, and our solid is in front of us, and that is our front view. Okay, again, swing to standard view, and then rotate, and pivot, pivot, swivel, pivot, and almost there. There you go. Whew. Okay, so that is our front view, and yeah, it does look like a rectangle because we have x equals 4 in front, and we have the plane intersecting x equals 4. We said it they intersect at z equals 3. Okay, y is going from negative 2 to positive 2. We get a rectangle. Okay, but hark, I made the surfaces a little bit opaque, or translucent rather, so that we can see through it. And check it out, we have something that looks like a parabola. Okay, and that's because, so I'm going to rotate it again. That's because we have this parabolic edge at the top. Okay, so that edge becomes looks like an exact parabola when we look at it this way. Okay, why is that so? That was the intersection of x equals y squared and z equals 3x over 4. Well, that's a direct substitution. If x equals y squared, then plug that in, so we get z equals 3y squared over 4. Okay, and that makes sense. Z equals 3y squared over 4. If z is 0, I'm sorry, if y is 0, then z is 0, 3y squared over 4. If z is 2 or negative 2, y squared is 4, 3y squared over 4 is 3. Okay, so it does pass through 2, 3, and negative 2, 3. Okay, so our equation is correct. That is z equals 3y squared over 4. Okay. Now, this can be scanned as either a type 1 or a type 2. It's a rectangle. Okay. There's only one small thing. Yeah, are we always entering through the bottom and exiting through the top over here, side to side? Okay. This is where the inner integral becomes very important. Okay, let's swivel it again like this. Okay, because remember, one of the ingredients in setting up the triple integral is sending the arrows through the solid. Okay, so I erased the green arrows. We need the arrows now pointing towards the positive x-axis. Okay, and that's where I have these arrows. Woohoo. So here you go, target practice. They're coming towards us when we're on the positive x-axis. Okay, so there's one. I have a couple more. Pew, pew, pew. Is there more? Pew, pew. More? Yeah. Is that the last one? No, there's more. That's the last one. Okay, that's already one of the surfaces. Okay, so I have a lot of arrows here because remember, they have to enter through one surface and exit through another surface. Okay, and therein lies the problem. What makes this somewhat of a tough problem? Okay, some of the arrows enter through the parabolic plate that we see here on an inclined. Okay, some of the arrows enter through the parabolic cylinder. Okay, the plate is flat, the cylinder is curved. Okay, so which is which? Okay, depending on where you enter the solid, okay, you will either enter through the cylinder or through the plate. Okay, what determines where you enter? It's the parabolic edge, okay, that we said has equations z equals 3y squared over 4. There they are. Okay, so if you enter below the edge, then you enter through the parabolic cylinder. But if you enter above the edge, then you enter the solid at the parabolic plate. Okay, so what does that mean? Let's do a type 1 first. Okay, y will go from negative 2 to positive 2. X will go from 0 to the parabola. I'm sorry, y. Y will go from 0 to the parabola, which is z equals 3y squared over 4. Okay? For those arrows, we will enter through the cylinder and we will exit through the rectangle, x equals 4. Okay? So fortunately, for both of them, for both kinds of arrows, we will exit at x equals 4. Okay? Small blessing. We'll take anything. Okay, but if your arrow is above the parabola, then you will be entering at the plate, which is this surface, and that surface is z equals 3x over 4. Okay, still exiting at x equals 4. Oh, wait a minute, I said z equals 3x over 4. So we have to solve for x as a function of z. X equals 4z over 3. Okay, so that's where we see these diagrams. And let's go to the next page. So this is where we have the type 1 scan. Okay, as we go left to right, we will have to start at z equals 0 and end at the parabola. Second part, we will still scan from negative 2 to 2, but we will start at the parabola and we will end at z equals 3. Okay, for here, the arrows will enter on the parabolic cylinder, which is x equals y squared. So yeah, we don't have to touch that because x is a function of y and z, and we will exit at x equals 4. Okay, so our integral has that form. There it is, that's what I said. Okay, so for the first part, y from minus 2 to 2, z from 0 to 3y squared over 4, that parabola. And then x will go from y squared to 4, okay, the parabolic cylinder to 4, okay? But for the second part, y is still going from minus 2 to 2, z from the parabola, 3y squared over 4, to z equals 3, but we will enter at the plate, okay? We have to solve for x in terms of z, x equals 4z over 3. We will exit at x equals 4. Okay, so now we're going to stay here for a little bit actually, because we're going to do a type 2 scan, okay, horizontal arrows this time, okay? Let's start over here. If you scan this with horizontal arrows, not a big problem, okay? Z is going from 0 to 3. Y is going from the left half of this parabola to the right half of this parabola, okay? That's this parabola. Yeah, that's not difficult. Solve for y. 4z over 3 equals y squared. So y is plus or minus square root of 4z over 3. No big deal. Okay. So we enter at the negative square root. We exit at the positive square root. Okay. We have a problem over here. Okay, because if you scan with horizontal arrows, we will enter the region, exit, enter again, exit again. I'm sorry, there are no, what do you call them? In and out privileges, okay? Like when you park and then you exit, sorry, you have to pay again when you come back, okay? So, what that means is we have to subdivide the lower half one more time, okay? So the rectangle into 2 pieces. Now the lower half, we have to subdivide again into a left half and to a right half, okay? But that's not so bad, okay? So z is going from 0 to 3. Y is entering at y equals negative 2 and exiting at the negative square root, okay? So that's for the left half. For the right half, we are entering at the positive square root. Z is still from 0 to 3 and exiting at y equals 2, okay? So we already know what to do there. Okay, so the final order of integration will have to be done in 3 pieces, okay? And we already know the equations of those boundaries, all right? So once again, we can recycle the innermost integral, okay? We already know that for the 2 sides, we are entering through the cylinder and exiting at x equals 4. So this is copied from the previous order of integration where we are below the parabola, okay? When we're above the parabola, we enter through the parabolic plate, exit again at x equals 4, okay? So the inner part is recycled, okay? So 3 parts, all of them are z going from 0 to 3, okay? Because all of our plates start at z equals 0 and finish at z equals 3. Okay, left half entering at minus 2, exiting at the negative half of the square root. Okay, so that is this one over here. Middle portion entering at negative square root, exiting at the positive square root. All right, there we go. Negative square root, positive square root. Final part, entering at the positive square root, exiting at y equals 2. Phew! Okay, so that is, of course, the last, and save the worst for last in this case. Entering at positive square root, exiting at y equals 2. Phew! Okay, so there we have it. Changing the order of integration in a triple integral. All right, that's video number 20. Next time, in our 21st video, we're going to do triple integrals, but using polar coordinates. Okay, so this time, we're going to give it a slightly fancier name. We're going to call them cylindrical coordinates. So, this is Jude Socrates signing off. Thank you very much for watching this video. See you next time.